Hi, I'm Taichi Tsuchida from Tohoku University, Japan. I'm going to talk about our work TetraForce. This work is also done by Kazuki Fujita, Kaori Ikematsu, Sayan Sarcar, Kazuki Takashima, and Yoshifumi Kitamura. Let me briefly talk about the background. Touch interaction has become a highly popular input method for most interactive devices, which provides intuitive interaction. However, the lack of input vocabulary has often been discussed as an important problem. One approach to solving this problem is the use of force. Applying force with the fingers is a primitive action that can be seen in our daily activities, and it can be applied without moving the fingers. Taking advantage of this capability, we believe that force can be naturally incorporated into input operation, thus expanding the input vocabulary and enriching user experience. Previously, many studies have been done on interfaces that extend the input vocabulary of touch devices using force, and they can be categorized into two perspectives. The first is the direction of the force applied consists of pressure force and shear force, and another is the target surface to which the force is applied consists of on touch screen and on other parts of device. Various interfaces using force have been proposed, and most of them can be mapped to this dimension as shown in the examples given here. However, limitation of this is that each combination of two force direction and two force targets has been implemented by a separate mechanism. Therefore, we believe that if each combination could be produced in a single device, this would provide a generic interface that does not require the user to replace the device according to the application, which would greatly benefit the user. Thus, we introduce TetraForce, a magnetic-based interface that enables 4 types of force input in a single device. TetraForce is a phone case-shaped device, and passively movable panel in 3 degrees of freedom is on the back of the device. This video shows the 4 types of input that our interface achieves. Pressure force on screen, pressure force with casing, shear force on screen, and shear force with casing. We implemented prototype device installed on a commercial smartphone. A movable panel is connected to the back of the smartphone, and a magnet is attached to the surface of the panel. So, direction and displacement of the panel are estimated by the built-in magnetometer and other sensors of the smartphone. Here is the internal structure built from the back of the smartphone. The panel and the case of the smartphone is connected with 5 pairs of push springs and flat springs. Thus, the movable panel provides kinesthetic feedback to user. This video shows a side view of the prototype. The panel moves vertically and horizontally to the smartphone. And this design allows the panel to move by force to each surface from the user, because user usually support device with their hands on the back of the device when user holds the smartphone. Then, I talk about software implementation. First, distinction between force on screen and force with casing is based on whether a touch input occurs or not. Estimation of shear force is referring to a previous implementation. Displacement of a magnet is theoretically estimated by using obtained magnetic vector. As for estimation of pressure force, we constructed a neural network model that outputs the probability of whether a pressure force input is applied, which is interpreted as a continuous magnitude. Feature values are data obtained from built-in sensors such as magnetometer, accelerometer, and gyro sensor. For the estimation of pressure force on screen, the vertical displacement of the panel differed depending on the touched position, as shown in this distribution table of force estimation caused by hardware limitation. So, our software applies touched position-dependent gain, and current implementation does not cover specific area, the right side and the bottom side of the screen. For the prototype I have just introduced, we conducted a user study to investigate the fundamental detection performance of our interface, measuring how accurately the actual interaction using our prototype behave as intended by the user. 12 students participated, and we asked them to perform a task of controlling on-screen indicator by applying a force at a specific strength for a certain period of time. Here is a little more about tasks. For each task for each input, a rectangle containing a target area and a bar is displayed. Target area is chosen from 4 areas which were mapped with force value and shown, and a bar moves in 1D by applied force. Participants completed the task by holding the bar in the target area for 1 second, and we measured the success rate of the input. This is a brief summary of the results of the performance study. The results show that the success rate was on average 97.4% for all types of input, and 98.7% except for the highest force level. These findings confirm that the prototype of our interface can obtain each of the 4 types of input with adequate accuracy without switching any mechanism for them. Then we conducted an interaction design workshop to explore the possible applications and usefulness of our interface. 12 human-computer interaction experts participated, and they studied and discussed application scenarios in which our interface would be beneficial. Each workshop was divided into instruction session and 3 discussion sessions about force on screen, force with casing, and combination of them. In each discussion session, each participant was asked to think of ideas for about 10 minutes, and then they had about 10 minutes to present their ideas and discuss the usefulness. Let's move on to the results. First, as the overall result, we obtained 188 ideas, including 137 ideas for either force on screen or force with casing, and 51 ideas for the combination of force on screen and force with casing. Here is a part of the results of force on screen. This table shows the obtained ideas categorized by force type and our own classification based on the advantages of the force-based input interfaces. For example, scrolling a document by shear force was mentioned as an idea that has the advantage of improving efficiency and reducing workload. And brake operation in driving game by pressure force was mentioned as an idea that has the advantage of increasing intuitiveness. Please see our paper for more detail. Here is the result of force with casing using similar categorization. For example, turning a page of an ebook by shear force was mentioned as an idea that has the advantage of resolving occlusions. And answering a call when hands are wet was mentioned as an idea that has the advantage of providing touchscreen-free input. Let's move on to the result of the combination of force on screen and force with casing. Here is the representative examples in the table. See the paper later for if you need more detailed results. As the example application ideas shown in this table, participants could come up with a wide range of ideas for applications, especially those requiring complex operations. We can say that the result indicated that there are sufficient needs for our interface that provide 4 types of input in a single device. Here, I will introduce the applications we implemented based on the application scenarios obtained in the workshop. This is a web browser application. In this application, user can scroll up and down pages by applying shear force on screen with less number of operations, and bookmark the page by pressure force on screen. Tab switching can be done by shear force with casing, and by applying pressure force to the back, a screenshot can be taken. Next, this is a first-person shooter game application. In this application, the user can smoothly switch between single-fired weapon by tap and continuous fire by pressure force on screen. And controlling camera can be done with shear force on screen, and moving avatar is done by shear force with casing. And by applying pressure force on screen, the user can turn on the mic and start temporary voice chat. Some limitations remain in our study. First, current prototype can barely detect pressure force on screen to a certain area. To resolve this, we are implementing a more robust structure using pantograph-based mechanism. Second, a magnet on our interface may have negative effect on some applications, such as compass in map application. Investigating this effect is one of the future tasks. Another limitation is that our performance study was limited to examining the fundamental input accuracy of the user. Investigating remaining variables are important future work. Here is a summary of our work. We propose TetraForce, a magnetic-based interface that enables 4 types of force input, combining 2 force direction and 2 force targets within a single device. In performance study, we confirmed that the user could input the 4 types of force input with practical accuracy. And in interaction design workshop, we obtained a total of 188 ideas, indicating that TetraForce is useful for applications that require complex operation.